Okay, so the last concept that we did not cover was simple harmonic motion. And simple harmonic motion could be if you can imagine this is a spring and it's bouncing in and out, or if you can imagine a pendulum that's swinging back and forth. So those are the things that we're going to be looking at. And simple harmonic motion is any motion that regularly repeats itself, which means that it does the same thing again and again and again. So if you can imagine a spring, I've misplaced my slinky, but if you can imagine a spring that is bouncing, in and out, as it goes in and out, it continues. Or if you did up and down, it would continue to do the same thing over and over and over. Same thing with a pendulum. And so these things have an equation, and the equation looks kind of complicated, but it's really not that bad. And that is x of t is equal to xm cosine omega t plus phi. And I'm going to explain what all these things are. Okay, so this right here, this is x max, which is also called the amplitude. All right, this stuff in here, we're going to kind of explain each piece. Omega is called the angular frequency, and that's in radians per second. And I know we're used to seeing that as omega as being angular velocity. And it's really kind of like that, except angular velocity is, measuring the angle that something goes through over a certain amount of time. This, you'll see when I draw the graph of this, how it really is. It's sort of like that because we make it akin to an angle, but it's not exactly the same thing. T is, of course, that's time. It's the same T as always. And then we have this phi, which this is what's called the phase constant or phase shift. And that basically, it's really kind of, it's relevant, but it doesn't change what the graph looks like. It just changes when I start looking at it. So if I were to graph the motion of a simple harmonic oscillator, this is what we get. And so if you said this is x and this is t, if we have a spring, if I pull a spring back and I let it go, it's going to go down, okay? So it goes down in the x. As time progresses, it goes down. And then what does it do? It goes past that point, and then it goes down here, and it slows down, stops. Then it speeds up, speeds up, speeds up. It's going as fast as it possibly can go. Then it slows down, stops. And we're oscillating just back and forth, back and forth. Or in the case of a pendulum, we're oscillating, let's see if I can do this. We're oscillating back and forth. And so you see when I get over here, this is when I get to my maximum high point. Here, here, here. This is when I get to my maximum the other direction, which is the maximum in the negative direction. And then when I cross through that downward position, straight up and down, that's these points, right? Or excuse me, right here, right here, right here. That's when I'm crossing through those points, okay? So your amplitude, since I've got this drawn in here, this is xm right there. That's the amplitude. How far away from that center point do I get? How far does my spring stretch out? How far is my pendulum pulled back? And that's my maximum displacement. Like, I'll never be farther away from where I am than I am at that moment. And remember that we do conservation of energy. And so we talk about, like, as a pendulum, if I pull it back to here, it's got potential energy. I let it go. It converts till it's all kinetic. And then it slows down, converts it back to all potential again. So we go all potential this way to all kinetic, to all potential the other way, to all kinetic, to all potential. And so if you did these, this is also the amplitude. It's just the other direction. It's the negative xm, okay? And you notice that we had this as the cosine function because this is the cosine function. Now, cosine and sine really look exactly the same. It's just where you start them from. So this is the cosine function. Omega is the angular frequency. And omega, that angular frequency, is 2 pi over t, big T. And big T is the period, which is the time to do one cycle. Now, as I'm going through this, you know, we said that this doesn't go through angles. I mean, you know, a pendulum does swing through an angle, but a spring doesn't. And so you can kind of describe your angular frequency as like, okay, well, I'm here at this high point, and then I take off, and I end up back here at that high point again. That is the time that it takes me to do that. The time here is equal to the period, because that's when I start repeating myself. That's when I do one cycle. And if I were to say, okay, on a cosine graph, what would this be? Well, this would be 0. This would be pi over 2. This would be pi. This would be 3 pi over 2. This would be 2 pi. So your angular frequency is basically like how fast I'm repeating myself, like how fast am I going through these cycles. And so I take that 2 pi, which is one cycle, and I divide it by the period t, and that tells me what my angular frequency is, like how fast I'm going through these cycles. And then of course that phase constant, that phi or that phi, that just depends on when I start looking at it. So if I started looking at it right here when it was passing through that, so I pull my spring back, I let it go, and I start timing it right here, then my graph would look like this. It would look like everything. It would start here. This would be the origin. And since I'm supposed to start up here, then my phase shift, this phi, would be pi over 2, because I just shift the graph over and I start looking at it there. So you don't really have to do a whole lot of concerning yourself with that, because it is kind of a moot point. It's just like, where do I start looking at the graph? It doesn't change what the graph looks like. It's just, where do I start looking at it? And so then I go to, well, if this is my position, then we know that velocity is the derivative of position with respect to time. So we're going to take the derivative of that. So xm is a constant. The derivative of cosine is negative sine, and we do chain rule here, so we do omega t plus phi times the derivative of the inside of this. This is a constant, so I'm doing it with respect to time, so I get omega. So my velocity is going to equal negative, I'm going to pull this omega out front, negative omega xm sine omega t plus phi. So my velocity is really, the graph looks the same because it's a sine curve. So it's a sine curve, but the amplitude on it is magnified. You know, like when you're looking at the sine curve of the velocity, then you know it's whatever the omega is. If that's a larger number than 1, then xm is going to be bigger than, or excuse me, then the amplitude of this whole thing, omega xm, it's going to be a taller curve. If the omega happens to be less than 1, then it's going to be a shorter curve than this, but it's going to be a sine curve. And so basically what that means is, where this one is going to have a peak and be at a high point, this one is going to be at 0, because when your cosine is at 1, your sine is at 0. So, and I'm going to have the opposite effect. So when I am here, I'm going to have a zero velocity when I'm out here at the peak. Then I'm going to get faster and faster and faster. Now remember, the slope of this line is my velocity. So as I get faster and faster and faster, and I get really, really fast right here, that's when I'm going to have a maximum on this thing. But it's not a maximum on the top. I guess you could call it a minimum, and it's going to go. So if I drew the sine curve that would go along with this, it goes this way, okay? And it goes that way because it's negative omega xm. So whatever, you know, my sine would be, if my sine would be positive 1 or whatever, then it's going to be negative 1. So it's just flipped over upside down. So this is what that graph would look like. And of course that phi, that could shift this over, that phase constant, it could shift it over to where it looks different. So whatever your phi would be on this one would be the same one here, and it would shift the graph accordingly. So if you shift the graph over to here, if your phase constant is pi over 2, when my cosine would be 0, that's when I'm going to shift it to right here, and this would be at its maximum low value. Okay, and the thing to remember about this is that your velocity has your maximums where your cosine hits your zeros. Okay, so I'm going to have my biggest negative velocity right here when that's 0. That's when I'm going to have this peak. When I get back up here, I'm going to have my biggest positive velocity right here. When I get to these endpoints, that's when my velocity goes to 0, because that's when I'm as far away. So like if I'm talking about a pendulum, I'm up here, I'm not moving, so that's 0. So that's 0 velocity. So I'm at my maximum x, minimum velocity. Then I'm going to let it go, and it's going to go faster, 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 as fast as possible. Slow down, slow down, slow down, slow down, stop. Faster, 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 as fast as possible. Slow down, slow down, slow down, slow down, stop. And that's simple harmonic motion. It's easier for me to show you a pendulum because I can do it with my pen. But if I had a spring that I could show you, and you can look up videos of this, and I'll probably put some links to other videos on the stuff I send you today. But that's how a simple harmonic oscillator works. And while we're at it, let's go ahead and look at one more thing, and that is acceleration. And acceleration is the derivative of velocity with respect to time. So I'm just going to derive this thing. So it's going to be negative omega xm, since that's constant, times the derivative of sine, which is cosine, omega t plus v, times the derivative of the inside of that, which is omega. So I clean this up a little bit. And that's going to equal negative omega squared xm cosine omega t plus v, or plus 5. Now, the thing about this is, look at this. This part right here, that's x of t, isn't it? The xm cosine omega t plus v, that's what we started out with up here. So my acceleration is really negative omega squared x of t. And so that means that when I have my biggest x, I will have my biggest acceleration, but it's going to be in the opposite direction. Okay? And that makes sense, because as my pendulum swings up this way, as I go up this way, I have my biggest force, my biggest pull on it to get it back, so the biggest acceleration, but the acceleration is that way. And then as I swing this way, I get up here, and the same thing happens. I'm at my biggest point, my biggest x in the negative, but my acceleration is going to be the biggest in the positive that it can be. And so that is how these two relate. Now, let's look at some pendulum stuff, or not pendulum, spring stuff. And let's use that to kind of go along with this. So we know that the force of a spring is negative kx, right? And we know that force equals mass times acceleration. So if the only thing you have acting is a spring, then negative kx is going to equal mass times acceleration, right? And from what we just did, we said acceleration is going to be negative omega squared x. Okay, and yes, it is x of t, but it's the x at that moment. So now I can take this, and I can cancel. I've got a negative here, and I've got a negative here, so I'm just going to go ahead and cancel this. So I get k is equal to m omega squared. So I can solve this for omega, and that's going to be the square root of k over m. And I'm going to use this little function, that omega is the square root of k over m, to find the period of a spring. And so we already said that omega is 2 pi over the period. That's angular frequency. So we're going to set that equal to these. We're going to set these two things equal to each other. 2 pi over the period is equal to square root of k over m. Okay, so this is all spring stuff. This is just a spring, not a pendulum. So then I rearrange here, and I'm going to let you trust me in a little hand waving here. Because what I'm doing is I'm multiplying both sides by t and dividing both sides by this. So I get this. And so this is the period of a spring. Okay? Now, if we look at a pendulum, okay, let's look at a simple pendulum. Actually, let's look at a different type of pendulum first. Let's look at a torsion pendulum. Okay, a torsion pendulum, because this looks like a spring, a lot like a spring, so we're going to just kind of keep it together. A torsion pendulum is like when you're a kid and you get on a swing set and you wind yourself up, and you twist yourself up, twist yourself up, twist yourself up, and then you let go and you unwind, and then you wind back up the other way, and then you turn around, you unwind. That's a torsion pendulum, something that twists up and it untwists and then twists and what have you. And so it looks like you'll have a string, and then you'll have something down here on the bottom, and it'll be rotating. Okay. Well, that torsion pendulum really, really, really is akin to a spring. And so it has an equation. And this is the way that you usually see it. And this is torque. So just like the force of a spring is equal to negative kx. This looks like a K. This is my futile attempt at the Greek symbol kappa. And kappa is called a torsion constant. It's like a spring constant. You know, a spring constant tells us how stiff a spring is, you know, like how much force it requires to stretch it out. Well, this is kind of the same thing, but it's in a twist. It's like how many Newton meters of torque do I have to exert on this thing to get it through, to go through this angle. And so this depends on the string or wire, whatever it is that you have. So, you know, if I've got something made out of string, that's probably got a very, if it's a thin string, it's probably a very low torsion constant. But if it's a very heavy, thick metal cable, it's probably a very high torsion constant. So the thickness of the material and what the material is made of all makes a difference on what that torsion constant is. And so we use that in place of a spring. And then this theta is the angle it's twisted through. So if I wind it up one time, that's 2 pi. If I wind it up 2 times, that's 4 pi. So it's whatever I twist it through, how much ever I displace this thing. And the more I displace it, the tighter I twist it, the more it's going to torque back, the faster it's going to go. And again, this is one of those things, like if you can imagine sitting in a swing set, the more times you twist yourself around, then the harder it's going to twist you back, you know, the faster you're going to go. So we use this and we say, well, this is like a spring. And so where I can kind of make my substitutions for that is I can say, well, this negative kappa theta is going to equal my I alpha, okay, because torque equals I alpha. And then your I is there, and your alpha is A over your R, right? I don't think, do I want to do that? Let me think for just 1 second here while I'm going over this and trying to relate these two, because they are one and the same. Okay, I don't do this thing. I'll leave this as alpha. And so then I say that, well, then my acceleration is going to be negative kappa theta over I. And so just like before, when I said my spring's acceleration was going to be kx over m, then I'm going to substitute these things in like I would a spring. And so the period of a torsion pendulum is going to be 2 pi times the square root of I, because I is the equivalent of mass in rotation, and then over kappa. So this is the period of a torsion pendulum. Okay, now another type of pendulum we have is a simple pendulum. And this is a mass on a massless string. And so if I have this, and it swings back and forth, back and forth, back and forth. Then I look at what is going on with this. So if this makes an angle theta that I pull it back to, okay, if I look at my restoring force, this is gravity, and this would be theta here. And so gravity has two components. It has the mg cosine theta, and then it has the mg sine theta if we considered this to be the direction of motion. Now, of course, it's not always that. It changes as it goes through, but at that moment, this is mg sine theta here. Of course, actually, it doesn't change the actual that. It's just that the theta changes as the pendulum is moving, but it stays at the same thing, the mg sine theta. So that's my restoring force. That's the force that is causing me to go back. Like, that's why a pendulum does what it does, is because it's got that force on it. And so if we go back and we say, okay, so the force that it's going to restore with is going to be mg sine theta or negative mg sine theta, depending on, you know, whether I have a positive angle or a negative angle. It's going to be opposite of. That's why I put the negative on there. So it's definitely going to be opposite. Okay, now there's a unique thing that says that it's called the small angle approximation. Let me move this up a little bit. And the small angle approximation says at small thetas, theta is approximately equal to sine theta. And I don't know the actual break of when you stop saying that. Like, I've tried to research that, and I've not found any definitive answer of when you stop saying that, but that you can't pull a pendulum back like 75 degrees and it function in a behavior that you would expect. Like, you're going to get some slack, it's going to get some bounce, and it's not going to work right. And so this small angle approximation tells us that, you know, if my angle's small enough, then this becomes mg times theta. Okay, and theta, if we call this, they call it x, like in your textbook, you'll see it as x. This distance here is L. So x is like my arc length, and x is equal to theta r, which would be theta L, right? Because s is equal to r theta, or theta r, however you want to look at it. And so because of that, instead of theta, I'm going to say x over L. So this becomes negative mg times x over L, okay? And so what I can do is I can then kind of write this as negative mg over L times x. And then it looks like the equation, because this is going to be my negative omega squared, right? And negative omega squared is equal to negative mg over L, and this is like, if I had, well, let's do it this way. Let's square root both sides. And so I get omega, which is k over m, and then over here I get the square root of mg over L. And then let's see, actually, let me back that up. Sorry. Let me back. I gotta think this through. I'm looking at the textbook at how they come up with this. All right, this is like mass times acceleration. Which the acceleration is negative omega squared x. And so mass times acceleration would equal omega squared x times mass. So that means that this stuff right here must equal omega squared. So omega is going to equal the square root of g over L. And that's also equal to 2 pi over the period. There we go. This is where I want to go. Okay. So MA is equal to negative omega squared x m. So we're going to make this equivalent here. So mass times acceleration, the mass would be in front. Here's the acceleration. So what I'm doing is I'm saying, okay, so here's the m. So this g over L here must be the omega squared. And then I'm saying, okay, so then omega must be the square root of g over L. And if omega is 2 pi over the period, then the period is going to be 2 pi times the square root of L over g. And that is the period of a simple pendulum. Okay. And then finally, the last type of pendulum that we have is a physical pendulum. And the physical pendulum is anything that's not, like, it could be like a meter stick. It could be like, a lot of times, and your axis rotation is right here, and so it can swing. So my pen could be a physical pendulum because the mass is not just like all concentrated out on the end. It's spread out somewhat, maybe not uniformly. Like, it could be uniform, it might not be uniformly. So, you know, it's spread out along the way there. And so if we look at this and we say, well, what's going to be our physical pendulum stuff? Well, okay, wherever that center of mass is, that's where gravity's acting. So we got the force of gravity right there, okay? And so we're going to pull it back some distance theta, or some angle theta, excuse me. And so that theta, the torque that this thing has is going to be I alpha, okay? And that torque is going to equal RF sine phi, okay? And that is going to be, excuse me, that R, I'm going to call that H, because if you remember, and in your textbook they call this D, but I'm going to call it H, because remember that H is the distance from the axis of rotation to the center of mass. And so I'm going to call that H, and again, I'm going to deviate from the textbook just a little bit, but I've got that. The force is the force of gravity, which is mg, and it's going to be times the sine of theta, because theta would be the angle between gravity and this r, because here's r, here's this, so that's going to be the same theta right there. Okay. Now, because of that, I'm going to use that small angle approximation again. It says sine theta is approximately equal to theta, and so I'm going to cut this down into mgh theta. Okay. And then I'm going to set that equal to the I alpha. But remember, this is going to be a restorative, so it's going to be negative. So it's going to go opposite to whatever is going on. And so then remember that the acceleration, so then the acceleration is going to be, it's going to be negative mgh theta over I. So that's my acceleration. Now remember that omega squared x is acceleration. So we're going to make that that kind of leap here, and we're going to say, well, this is this right here is going to be my negative omega squared. So omega is going to be the square root of mgh over I. And then we're going to set that equal to 2 pi over the period. And then we're going to solve for the period, which is going to be 2 pi times the square root of I over mgh. And so that is the period of a physical pendulum. And that is pretty much like the gist of that chapter. I mean, it's very, very, very pared down. But That's the most of simple harmonic motion. The thing that I think that you would, obviously you don't need any of it because the AP test is over and you're done with it. But the things that they typically, let me bring these back. Typically on the AP test, the period of a spring is important. And the reason that a period of a spring is important is a lot of times they'll ask multiple choice questions on stuff like this. Because if you look at the period of a spring, spring only cares about what mass you put on it and what the spring constant is. The spring doesn't care where you put it. So in theory, a lot of times they like to ask the question, they say, okay, a spring on Earth has a period of 2 seconds. We take it to Mars and we hang the same mass on it, and what's the period there? And they'll give you a lot of yada, yada, yada. Well, the acceleration due to gravity there is this, and blah, 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 blah. But the thing is, the spring only cares about 2 things. How much mass did you hang on me, and what is my spring constant? So as long as I'm hanging the same amount of mass, and I've got the same spring, it doesn't matter where I take it. I can take it to the moon, I can take it to Mars, I can take it wherever, and I'm going to have the same period. Now, a pendulum, a simple pendulum, I'll back this up. Okay, a simple pendulum, that's another one that's really important, and they like to ask about this one, because a simple pendulum does care where it is. And you can actually find, the acceleration due to gravity at a point if you're given a simple pendulum. And because you just measure the length of the pendulum and measure the period, which is how long it takes to do one cycle, and you can find G. You can extrapolate back and find G. So I'm going to give you guys like 1 or 2 problems that involve this stuff and let you work on those. But it's not as complicated as it looks, but you can really wow your friends, especially with this stuff. You can make them think that you know so many different crazy things, but it's just Greek letters and taken derivatives, just a little calculus. So that's simple harmonic motion.